which actually is kind of the opposite in that it's very well suited to linked lists and not very well suited to arrays. It's called merge sort. Merge sort is based on the observation that it's possible to merge two sorted lists together into one sorted list in linear time. In fact, how do we do that? One way to think about it is as a selection sort on two queues. So let's just suppose that we have two sorted lists and we express them as queues. So I'll call them Q1 and Q2. Also, I'm going to create an empty queue called just Q, which is going to be the destination where I put all the sorted items. Now, as long as the input queues are not empty, what I'm going to do is I'm going to look at the item at the front of Q1. I'm going to look at the item at the front of Q2. I'm going to compare them. Whichever one is smaller, I'll take it out and put it into the output list queue. So let's look at the item at the front of Q1. Let's look at the item at the front of Q2. And whichever one is smaller, compare them. Whichever one is smaller, move it from where it is now to Q. Eventually, one of the two queues is going to be empty, and then the other one's not empty. You just take all the stuff that's in the non-empty queue and you concatenate it to the end of the output queue. You have sort of seen this before. Again, this is something you've done for homework 5. You'll recall that in homework 5, you implemented a union operation where you compute the union of two sets, and we asked you to do it in linear time. So if you did it right, you essentially did this, walking through the two sets, checking which one has a smaller item at the front of the queue, and moving that to the output queue. There's just one difference. When you were computing the union of sets, if there was a duplicate item, meaning if there was an item in both Q1 and Q2, you would only have one copy of that in the output. Here, we're not doing sets, we're doing sorting. So if you have multiple copies of the same key, you copy all of them to the output. You don't get rid of duplicates. So one way to look at this merging routine, by the way, is this is a selection sort. So we're just doing selection. We're finding the smallest item, and we're moving it to the end of the output list. But selection is really fast in this case because we're sorting two sorted lists rather than sorting a big unstructured mess of numbers. And so now selection is fast enough to actually be worth using, because you can merge two queues in linear time. Once you have the ability to merge two queues in linear time, or two sorted lists in linear time, Then we can build a sorting algorithm out of that with using this as a subroutine. Merge sort is what's called a divide and conquer algorithm. It is recursive. What merge sort does is it divides your unsorted list of numbers into two separate unsorted lists of numbers in no particularly interesting way, just divides it into two sets. It recursively sorts each of those two sets separately, and then it merges them together into one sorted list. And that's the conquer part, is when you remerge the two lists that you divided. So here's the actual algorithm. We start with an unsorted list called I for input of n items that we want to sort. We're going to break I into two halves. So we're just going to take the first half of the items and call them I1. We'll take the second half of the items and call them I2. So each list has about n over 2 numbers. If you want to be precise, the first list will have n over 2 ceiling numbers, and the second list will have n over 2 floor numbers to sort. So if n is odd, well, obviously you can't divide it into two exactly equal piles, but you get as close as possible. Then we're going to sort I1 recursively with merge sort. Let's just assume that merge sort works. So after you sort it recursively, you get back a sorted list of the same items, which we will call S1. And then we sort I2 recursively, yielding a sorted list that we will call S2. And finally, we will use that merge routine that I wrote above to merge S1 and S2 together into one sorted list. And I'll call that sorted list S. That's the output. And that's merge sort. So let me show you a pictorial way of imagining what this algorithm is doing. Let's suppose that I have a list of 8 items. Let's not worry yet about what particular numbers I'm sorting. We're going to take those 8 items and break them up into 2 groups of 4 and do a recursive call on each of those 2 groups of 4. So there's a group of 4 here. And there's another group of 4 here. And we will recursively call merge sort on those. And what do? Well, they take those 4 items and break them up into 2 lists of 2. And recursively call merge sort on those. Now we've got lists of length 2. We call merge sort recursively again, breaking this all down to lists of length 1. In merge sort, the recursion bottoms out when you get to a list of length 1. So a list of length 1 is already sorted. You can stop there. What I've just drawn here on the board, this is a tree that shows you the structure of a sequence of recursive merge sort calls. So it's a little bit like a game tree. This is not a data structure. You do not actually create a tree data structure. Just like when I was drawing the pictures for game tree search, this just tells you what all the recursive merge sort calls are. So when you get down to the bottom, let's suppose that the numbers that you wanted to sort were 7, 3, 9, 5, 4, 8, 0, 1. What happens? Well, after we get down to the bottom of the recursion here, we go up a level and we merge this list 7 with this list 3 using that selection sort that I showed you. And so now we have a merged list 3 and 7. The same thing happens here. I'm going to merge these two lists, and that'll give me a sorted list 5, 9. I backtrack up one level, and now I can merge the list 3, 7 with the list 5, 9. So I start walking through both lists. Which is smaller, 3 or 5? 3. Which is smaller, 5 or 7? 5. Which is smaller, 7 or 9? 7. And then the 9 goes at the end. And likewise on the right-hand side, merge 4 and 8, you get 4, 8. Merge 0 and 1, you get 0, 1. Merge those two lists, you get 0, 1, 4, 8. Finally, at the very top of the recursion, the very first merge sort call merges the two big lists into 0, 1, 3, 4, 5, 7, 8, 9. And that is how merge sort is done. What about the running time of this? Well, let's count how many levels there are in this recursion tree. It turns out that if you have n items you want to sort, then you're going to get 1 plus, well, you take the base 2 logarithm of n, and you take the ceiling of that, and that tells you how many levels there are in this tree. So that's a really useful piece of information, because at every level of the tree, we're doing the same amount of work. The time it takes to merge two lists is linear time in the sizes of those lists. As you go down the tree, you get more and more lists, but the lists are smaller and smaller. The total amount of work at each level of the tree is always linear work per level. And that is why merge sort runs in order n log n time. Any questions about merge sort? If the length was an odd number, then things still work. So if you have seven items, then the recursion will give you 4 items here and 3 items here. And then 2 and 2, and 2 and 1. And then these ones will bottom out at a different level. And that lonely one on the far right will stop one level early. So, the leaves are not always at the same level. They can differ by 1 level, but it still works out in the end. And that is why when I wrote the number of levels, the reason I wrote a ceiling here is because if n is not a power of 2, that's going to be some fraction. No matter what list you have, it's always, yeah, it is. Okay. So, good point. It is theta n log n, both in the best case and the worst case. Uh-huh. Oh, sorry, what was the last thing you said? No matter how well sorted the data is, yeah, if you have data that's already sorted or partly sorted, this does not take advantage of that in any way. So, yeah, you're right. One thing that differentiates merge sort from the other algorithms we've looked at is it's really not an in-place algorithm. People have tried to figure out versions of merge sort that you could run in place, and they just have turned out to be terribly, terribly complicated. No researcher has ever figured out one that would be simple enough, a simple enough in-place merge sort that you'd actually want to use it. So, merge sort. If you are sorting an array with merge sort, you usually use an extra array that is also of linear length to temporarily hold the result of a merge. So that's kind of a disadvantage of heap sort, is if you want to sort arrays, then the best way to do it in practice is to use twice as much memory as what heap sort would need. Any questions about that?